Okay, so the goal of experimentation in computer science is all about trying to prove your claims. So in your paper, in your research, you have some claims. First of all, that means you have to actually have some claims to prove. If you don't know what your paper is trying to prove, you're probably not going to get there. You're going to have some evidence to back you up. And evidence that's almost always going to be the most useful is stuff that's statistically significant. We'll talk a little bit about that this class, and then next class we're going to give the statistical significance. We want to have well-constructed, influential, considering all the things that can go on set of experiments, which is what we're going to talk about today, that are then discussed and from which you can draw a set of conclusions. Right? So today we're focusing on how do we talk about what makes good experiments and how do I design good experiments for computer science, modulo the statistics piece, which we'll get to in the next week. So I don't actually have books for this class, but this is a book I do recommend, Empirical Methods for Artificial Intelligence from Cohen. This is it's relatively old, from '95, but its ideas about what does it take to make good experimentation are actually, I find, very compelling, in part because they have a bunch of material that shows some examples, which I'm going to go through most of today. So in fact, you'll get what I consider the key highlights out of the book today.
Can I ask a question? Sure. And I know it's a bad question, but I'm going to ask it anyway. So one of the things that I find is that sometimes I just want to experiment because I want to see what happens.
Mm-hmm.
And I know that that's not a good experiment, but probably good for curiosity. Is there an appropriate way that upon doing this, small experiments or classifying them as small experiments that are leading up to forming a hypothesis?
So it's a good question. I should lead to the next slide. So, so I, in fact, draw the distinction between doing an experiment and experimentation, right? So,
I call them science projects.
I'm fine calling them experimentation. Experimentation is exploring and doing new things and trying to look for things in the real world. Right? So, in the physical sciences, there's a lot of experimentation, and there are experiments. So, experimentation is doing things that help me explore the world. In the computational world, I can explore all kinds of things. And I can look for patterns and observations. One of the papers we had last year at NERPS came out of one of my students looking at data from a completely different experiment that was out to prove one thing, but looking at the data and exploring it in such a way that led us to a new hypothesis that led to a new experiment where we went out to prove our claims. So it's a good question in the sense that experimentation matters. Exploring and thinking not just I want to prove something is not the only thing you do with your computers. You want to explore those ideas. Tinker, see what can happen, what can I try? And then you want to turn that into a hypothesis and get to a claim. So from experimentation, you come up with evaluation, begins with claims. Now I know what I want to see. So we hypothesized, for last year's paper we had last year, that the magnitude of deep features in deep learning representations was actually related to the uncertainty of the classifier. That was we saw some of that, but it wasn't a perfect correlation. But then we said, well, now we can turn around and make it a hypothesis and say, we're going to make it have that property, and that will improve the system performance. So we were just noticing that really bad, blurry images tended to have smaller magnitudes than very crisp, clear images. It's an observation you get during experimentation that you turn around to a claim. So, but for an experiment, so did I answer your question?
I think so.
So the one thing I didn't answer was after I wrote it. One of the most important things about experimentation is making good notes about your observations. Because in fact, my student had noticed this, but he hadn't actually said, we can use this. But when we were discussing it, he said, well, I had this observation. It's like, and then we'll go down this path. What can you do with this observation? What does it mean? Where does it go? So observations and taking notes about them are an important part of that characterization of experimentation. Another paper we're working on now came about because 6 years ago, I had an observation of something that happened with a polarizer. I wasn't doing anything special. We were just happened to be playing with LCD shutter glasses, and I noticed something, and I made notes about it. And then a couple of years later, I said, maybe we can actually exploit that to do something. Right? So it wasn't just that I noticed it. It was like I noticed it, I took notes about it, I looked for some information about it, couldn't find anything about it. So then I did a little bit more research. Before I go to the experiment, I do research. Has anyone discovered this? What's going on? Right? I routinely Google stuff all the time to sort of see what's known, is that well known? I literally have a hypothesis in my notebook. I have a file for ideas. That high blood pressure might be affected by mouthwash. From personal observations, and I've been now doing various experiments at home where it's like, I measure my blood pressure, I go use mouthwash and brush my teeth, and I come back and my blood pressure is 8 points higher. And now it's like 6 times having done that, and it's 8 to 10 points higher every time. And I've started Googling it. So observations, but noting them, and sort of like being, right, was it Pasteur's, right? Chance favors the prepared mind. Right? If you're looking for things and taking notes about them, you will be in a much better position when you're doing your experiments. So take notes. So coming back to evaluation. So now I've had these hypotheses. I go start running an experiment. And oddly enough, in my view, and this is also consistent with Cohen's, right? If I want to evaluate, the goal of my experiment is evaluation, right? Understanding those claims and being clear about what they are is critical. It is probably the most important and often the most neglected part of coming up with an experimental plan. What I want to measure depends on what you want to know, which depends on what you want to claim, right? So the goal is not to measure a bunch of stuff and then figure out the claim. That's really bad science. Your goal is to say, here's my claim. I will go measure stuff. Now, your measurements may not be consistent with your claim. Then you have to revise them and iterate. So good claims to me are the same as good goals. From a management point of view, goals should be smart, specific, reliable, measurable, SMs. Measurable,
relevant,
actionable, or attainable, reliable, and timed. Right? And experiments, in my view, pretty much follow the same thing. Right? So claims like X is bigger, faster, stronger than Y, very clear claim, right? I can measure things about X and Y and it's figured out. Right? Another precise one, X varies linearly with the range we care about. X and Y agree on most test items. Most is a little fuzzy, but it's still possibly there. It doesn't matter who uses the system, so it doesn't matter if they're experts or novice, right? There's no system effects. Those are still measurable things. My algorithm scales better than yours, relationship between size and run type. All of those are claims. They're all falsifiable. Another important part of what anything we would do in experimentation is deal with falsifiability. A non-claim is, I built it and it runs fine on some test data. Now, no one phrases it that way, but see, I built it and I ran it on these benchmarks and here's the time it ran at, right? That's not an experiment.
I thought I ran it against 6 test sets, it failed on 5 and it succeeded on this one.
So I chose the test sets to report on that it does work on, and I ignored all the others, right? None of those are really experiments. So experiments are generally, right, a comparison. Now, which of these is not an algorithmic comparison? There is one of it is not a comparison across algorithms. Fourth one, it doesn't matter who uses the system, right? So I can have an experimentation that is about how humans interact with my system, and that's perfectly good as well, right? So humans will find this to be able to do this, humans can complete a task in this much time. I can come up with a whole bunch of things that are just about my system, but the hypothesis has to be something that's meaningfully measurable. If I say people can run it on data, that's not really very meaningful. This one is really saying experts and novice don't see a difference in effect. That's more measurable. And now I'm actually comparing 2 people in the same system. So there's still a comparison that goes on. So let's look at a case study. We're going to go through 2, but we'll start with this one. Comparing 2 algorithms. So this is a straight up standard computer science thing. This is not actually AI, but it makes a nice simple example. So it comes from, Yeah, 2 algorithms, 2 processes, right. So this is a simple task. I want to schedule processors on a ring network. And jobs are spawned as binary trees. So I have a task, I can spawn off 2 new tasks, I can spawn off 2 new tasks, and so on. So this is a classical problem for distributed processing. I have a bunch of processors. In this case, they're on a ring. So they all talk to each other next to each other. And I want to answer a simple question. Here's an algorithm. I'm a binary, it's a process you spawn as binary trees. I'm going to keep one, and I'm going to send one to my neighbor, either my left neighbor or my right neighbor, arbitrarily. I'm going to flip a coin, randomly assign that one task to me and one goes to my neighbor left or right. So the second algorithm, intuitively a much better algorithm, I'm going to keep one and send one to my neighbor that is the least heavily loaded. So my neighbors have some amount of work they're doing. I'm going to figure out which one is doing less work, and I'm going to give them the extra work. and I'm going to take on the work myself. So the first one is just COSO, the other is COSO star. So theoretical analysis, right? We can talk about these and what's optimal and one's better, whatever. But they're all based on making various assumptions, right? So the real question that is hard to answer is, for a real problem, how unbalanced are these trees? So it turns out if I give one to my least loaded neighbor, and the trees are balanced, it's better. But if the trees aren't balanced, it's now hard to answer. How unbalanced? What's going to happen? So this is a straightforward empirical thing. So now, is there a claim here? Can you think of what a claim might be? So the utilization of everybody's about 50%. Well, that is a hypothesis. It's not a very precise one for this problem. Right? What do you think I want to do with this?
COSO alpha is more efficient than COSO.
Right. So the new algorithm, COSO star, is better than COSO, right? So the hypothesis is better. Now we have to figure out what that measurement is. Is it utilization? Is it throughput or whatever? So a hypothesis is that COSO takes longer than COSO star because COSO balances loads better. Okay, so now this is a good way of formulating a claim, right? It doesn't just, the first part would also be a claim. COSO will take longer than COSO star. Okay, that's a claim, but it's, from a research point of view, it's not a very good claim because it gives me no insights as to why. I can measure it a bunch of times, but I have no insights as to what's really going on. Now, the other reason it's not a good hypothesis, balances the load better, is really our hypothesis, right? If you think about why did I say I'm going to set it to my least heavily loaded neighbor, it's like, well, because they have less work to do, therefore that should be a better reason. Right? So we want to answer that question by making our hypothesis with this because phrase, right? And that's now a hypothesis about why it works, not just that it is, but why it works. And that's the more interesting research hypothesis. This is a better hypothesis than just saying one beats the other. So from an experimental design point of view, we're going to talk about various types of variables. So in this experimental design, our independent variables are which algorithm? I can independently choose that if nothing else depends on it. The number of processors, the number of jobs, the probability that a job will spawn. Right? All of those are independent variables because I can set them to any number I want. And a dependent variable is something that I cannot set but happens because other things are set. So the time it takes to complete jobs is a dependent variable. Now there are other dependent variables. So if I, for example, talked about processor utilization, that would be another dependent variable because it depends on all these other things. Now, I could actually, sometimes in this problem it's really hard to think about, but if I wanted to talk about time to complete jobs as being an independent variable, so there are scheduling problems for which I say, here's the schedule. And now the question is, how many jobs can I fit? Right? So the number of jobs could have become the dependent variable, and the time to complete jobs could have become independent. But I can't set them both. Either I set one and compute the other or the other one. Now, in this particular situation, because the scheduling problem is binary trees, right, I can't really control the number of jobs, right? Once I have the number of things and the probabilities, they all start spawning. So even here, the number of jobs may itself not be a truly independent variable because I can't independently say I have n processors in the node. And the probability of spawning a new job is this often per second. That also determines the number of jobs. So, but we're not going to get into great details for this, worrying about what is or is not. It's easier to just think of that as an independent variable. Now, when we want to look at variables, we're going to talk about some standard terminology. So independent variable is something you manipulate in an experiment, or something supposedly a causal factor that you can't actually manipulate, such as gender, right? Sometimes called a factor. So people will sometimes in their writing talk about independent variables and factors. Factors are things I don't get to choose. They are. Independent variables I can choose. Now, gender is not something that in an experiment for computer science we see a lot, but if I'm assigning people to various human factors groups, then I might actually care about gender as an independent variable. I actually find it good to separate this idea of independent variables and factors. When people talk about factor analysis, they mean all of the independent variables. But I like to think of independent variables as ones I choose, and factors as though things that exist that I try and deal with, but I really don't get to choose them. Right? If no women show up in my computer science class, I can't assign somebody and say, well, you're the woman today. No, that just doesn't work, right? I can only partition my data, right, which is an important thing from a factor point of view. Independent variables, I really get to choose them. And then I can talk about dependent variables. They indicate some form of dependence of a causal effect on factors representing independent variables. So this is a classic kind of drawing for. So these two things, factors 1 and 2, these are inherent factors. So the next things are independent variables that may or may not be dependent, that are causally dependent on those factors. So in a real world problem, the number of jobs is not actually an assignable variable. The number of jobs depends on the work I'm doing, right? So they come from the real world problem. In this case, so X1 might be the number of jobs and F1 is the actual underlying task. In this case, we're going to simplify them and ignore that factor. We're just going to assign them as random things. The number of nodes in my ring are, again, there's a factor, like literally, what's in my ring, right? We don't get to choose those as an independent variable, but in this experiment, we're going to experiment with design. So it is common to actually never assign the factors. They just happen to exist. But they always tend to be there for any independent variable. There's often in the real world setting a distinction between them. So we've described our independent variables, and we'll come back to why we need those in a second. But now let's say we just ran that experiment. So we ran COSO, the dumb algorithm, and we wrote COSO star, the load balancing algorithm for various numbers. And we look at what is the mean time to complete their jobs. So they have some number of jobs, and then we spawn off at some probability, so we get some total number of jobs. And now we look at those. So here is the sometimes non-intuitive initial result. COSO takes 28.25 milliseconds, and COSO star takes 29.35 milliseconds. So the algorithm, that was the dumb algorithm, just randomly assigned stuff, was 4% faster than the smart algorithm COSO star. Now, this difference turns out to not be statistically significant. We'll talk a lot more about that in the next couple of classes, but what do you think happened here? How could this clearly better algorithm balances the load by saying, give the work to my less loaded neighbor? How is that worse than the simple algorithm?
The conditions that you decide your evaluation of the decision, which is the more complex part of the algorithm, added time to the process.
So
that's one theory.
That's one hypothesis, right?
Hypothesis.
So this is where, as I said, experimentation is happening. We had a hypothesis, right? We actually haven't figured out the why part yet, but the first part of the hypothesis is that COSO star was better than COSO already failed. Right?
Under the conditions.
Under the conditions, right? But so the question is, well, maybe it's this hypothesis. So you can have more hypotheses. But as I said, one of the things you want to do when you're doing experimentation, we were running an experiment, but you want to look at stuff, you want to have observations. So hopefully I didn't just measure that time. Because if I just measure that time, now I have to go do no experiment. I can try and go to
It's okay.
It's K. It's got a K, so as I said, if I get the first letter, that's all I can see in my head. So, I can see your face. So your hypothesis that basically is the overhead of trying to decide is what's killing us. So how would we test that hypothesis? Not you, somebody else, right? So if the hypothesis was the overhead is what's killing us, how do I test that hypothesis?
Measure how much overhead there is.
Right, so I can measure the overhead, and then I can measure the rest and figure out what's going on. So any other hypotheses, what might be going on beyond the overhead? Right? This is tough. As soon as you generate a hypothesis, you're often stuck. That's the hypothesis. There's others. Any other hypotheses?
Just if you didn't have enough workload to really challenge the system, then it would be more efficient to pay attention to who's less busy rather than just making it.
Right, so if in fact there is almost no workload, right? So if the workload isn't high enough, right? So effectively, if my job queues are starving because there's no work for them to do, then this algorithm might not make a difference. So the combination might actually work out. So let's look at the time series of the queue lengths of the different processors. So you choose some random processor I, and if I measure enough, again, good experimentation generally measures a whole bunch of variables that you may or may not need, but you want to measure them anyhow. So when you're designing your stuff, log all kinds of stuff as long as logging doesn't pierce you too much. So queue length is pretty trivial. So here's the COSO algorithm's Q length, and here's the COSO star's Q length. So coming back to John's comment, right? Roger, not even close. Oh, right. Unless the processor is starved, which is when the Q length gets down to 0, right? I always have people in my queue, so left and right doesn't really seem to matter much as long as I'm doing that. So the load balancing advantage, right, isn't going to outweigh the overhead. Right? So I didn't have to even measure the overhead, right? It's just sort of natural, right? If I'm always got stuff in my queue, then it doesn't really matter. So COSO star is not better than this because I didn't really need load balancing. I always had enough load that I wasn't really getting it. So coming back to our variables, independent variables, right? So in this case, what is Q length? Is it a dependent variable or an independent variable? It's independent. Okay, so that's not what it means. It means I'm already in the queue for this processor. So I'm waiting on this processor. So it's not that I have to wait and then get assigned. I'm assigned, I'm in the queue. Does that change your interpretation? No, each processor has a list of these are the jobs I'm going to work on, right? So I can have 20 jobs waiting for me to work on.
Variable which the researcher controls.
Well, so I might want to control it, but can I control it? So I can easily control the maximum queue length. I can say this is the maximum I can have. But what's actually in the queue depends on what's running and what's not. So it's a dependent variable. So this becomes problematic because when I'm looking at this, right now our hypothesis is being affected by a dependent variable, right? So from an experimental design, if I wanted to, I can't say my Q length is this, or could I? How can I affect a dependent variable?
Load processes. You can force load processes.
I can make more processes. So if I look at a dependent variable like y, right, I can look, if I've drawn this causal diagram, right, I can say, well, what affects y? And I can look up at either x1 or x2 and say, if I want y to do this, how do I make it do it? So if I increase the number of jobs, or I increase the probability of jobs firing, right, I can make more things happen in the system, and therefore give it a greater load to make it breach that. So this is the other reason it's useful to look at what's dependent and what's independent, because they give me a way of, especially if I draw it out as a causal diagram, of saying, here's how I get what I need to have happen. I go back and do it. With enough time, you can always reason about that, but it's easier if you've been a little bit more formal in your process and make that forward. So now, as we said, the hypothesis didn't work out, right? COSO was a little faster than COSO star, but I also said this difference is not statistically significant. So another thing we could look at, so now we have one hypothesis that has to do with load balancing. We're now going to look at another hypothesis or related. And now I can look at this and I can say that COSO is statistically no faster than COSO star. First of all, why is that a valid hypothesis given that I just showed you that COSO was faster than COSO star? It is different, but also notice that, so rather than saying, and this is an important thing that will show up in lots of experimental design, but especially with statistics, right? So instead of having the hypothesis be that COSO star was better than, now we're saying it's statistically no better than, because our goal is to reject hypotheses. So we want to be able to reject stuff. So that's part of what happens. But another thing to look at in terms of the system is to look at, and I forgot this. No one called me out on this. This is a classic thing that people get wrong all the time, and I put it up there just to sort of answer. Did anyone else notice anything different about this comparison? Which is pretty much the way it shows up in the paper.
You have multiple lines
Well, those are just different runs.
Right. But you don't explain what those are.
That's true, I didn't explain it, but each of those are different runs. But there's something far more fundamentally bad about this presentation. The axes, right? This one is 0 to 50. This one's 0 to 30.
Oh, I never thought about that. That's terrible. Cannot unsee.
Oh, they weren't labeled, but this scaling problem is and this depends on what you want to show. But when you look at it like this, it's like, yeah, COSO, yeah, they're about the same on at the top, but this has got a lot shorter ones, right? But realistically, this goes up much farther. So COSO actually has much worse times as well as much shorter times, whereas COSO star is far more consistent. Right? So if I made that observation looking at this, then I might have a different hypothesis, which has to do, but of course it depends how you present the data, right? When you do automatically scaling graphs, which is common in a bunch of these tools, right? They always just lay out the same size, rescale things. Be very careful how you interpret that. So you might also look at this and have a different hypothesis, besides the fact that it's because it hits 0. What else might be going on? This one's more subtle.
I'd like to see the line where the starvation mode happens on bold. Just like for contrast.
For contrast, yeah. So that's an interesting experiment. You could run that one. So I will go ahead and actually tell you the other hypothesis to look at this, which is a classic problem for things when you see very different spreads of data. One is that this one is somehow affected by outliers. In fact, to be honest, this is an outlier. This is the outlier that happens when you hit 0. But overall, this has just got a much higher variance. There's a lot more variation going on as opposed to just variance. Variance is a particular statistical term. So it's possible that what's really happening is that there's a few outliers that are causing you problems. So if I look at the times to complete in terms of seconds, right, the frequency of how many of those happen, right, there's a whole bunch of things that complete really fast, and there's a few things that take a little bit longer. Notice, again, difference in scaling, 80 and 70. So this one has a whole bunch of jobs that compute really, that complete faster than this. But as I go out here, here's 20, right? There's a few more points far to the right on COSO star. So there's some jobs here that are much longer than any job we saw over here. Right? These don't quite get out to 30. That gets out. There's a few more out there. 1 or 2 outlying points can destroy a mean. A mean is not a robust estimate. 1 large value or 2 large values, the 2, I should be pointing over here. Right? This extra large lump here compared to that one is enough to shift the mean. So we know that outliers dominate the mean. So any test of is this or is this not significant fails because there's such a big variance. The system can't actually decide is COSO better than COSO star or the other way around. It can't decide anything because there's just too much variance going on. And this is a classic problem. So when I'm looking at things, I'm going to come back again to this independent variables. Which variables do you think determine variance, the variation we're seeing? Well, the dependent
F1 and F2.
So the dependent variables are the ones we measure, and they're the ones in which we see variation. So runtime is a dependent variable, right? So the one thing that's not shown in this diagram. So the way I described it, we talked about like the number of jobs in the processes. There's one other major factor here, which is sometimes not even viewed as an independent variable, which is it might literally be the algorithm itself. Right? So the algorithm could be driving the variance, right? Or whatever. But if I want to go back, now I'm stuck. Right? Our original hypothesis failed. We've seen this variance. We've seen that their job queue is running out. So now it's time to do more experimentation. We have a couple of hypotheses. So maybe we can go out and we can look at the data again, and we can say, this mean thing is what's causing me a problem, the outliers. So if instead of computing the mean, I compute another variable, the median, right? Which is I take all the sort times, I sort them, and I choose the one in the middle. This is a much more robust number because one really long-running job doesn't change it, right? I have to change a whole bunch of jobs to affect the median. And you'll now see that for median, COSO takes 498, and COSO star takes 447. So with the mean, my experiment didn't show anything interesting, but with the median, now at least I'm going the direction I expected for my hypothesis. Now, another question whether or not this is statistically significant, we'll come back to that in just a little bit. But as we're starting to look at that, it becomes important to recognize that a small change in my hypothesis, when we said it was faster in the original hypothesis, we said because whatever, we didn't say how to measure faster. A critical issue in experimentation is always, what's the right metric? Should I measure the mean, the median, the absolute deviation? There's a ton of things I can choose to measure to say what matters. So if I wanted to argue for mean, why would I argue for mean? I'm scheduling jobs. Why is it meaningful to say I care about the mean time? No, the mean is not the range. That's the range is the min and max, right? So the mean is also when people talk about the average wait time. Yeah, say how it performs an average, right? In fact, average is what more people think about. Okay, median is a much harder thing to get people to think about. So by default, I would say most people would think mean is the right thing, right? Right? So
there's at least 3 statistically valid definitions for average.
Mean,
median, and mode are all valid definitions of average.
No, they're all meaningful definitions of the central tendency.
Okay.
Average is a mathematical definition, is mean.
Is it?
Yeah. So the mean and median are all, here's the center of the distribution in a meaningful way. Mode may or may not be, but I don't think, so in a unimodal distribution, then the mode is a pretty good approximation. In a bimodal one, not so good.
Gaussian is all the same.
So when you're looking at your things, when you're trying to figure out what's going on, right? Again, it's useful to think about the dependent variables. What's causing the variation? It might turn out, and in good experimental design, we'll come back to spend a lot more on this, controlling the independent variables to affect the dependent variables. So we're seeing all this variance. We're seeing Q times running down to 0. Both of those we can get back to and say, okay, how do I adjust the independent variables to make that happen? There's another question, if that's actually helping understand the problem. We'll keep going down this path, right? So how are we looking at where we are now, right? So our hypothesis was that COSO takes longer because it balances the load better. Mean COSO time is shorter than COSO star. Median is longer. So there's no evidence to suggest that load balancing really helps because there's almost no processor starvation in this experiment, right? Most of the time, all the processors are completely busy, right? So that was the other hypothesis, right? So now what are we going to want to do? So we've analyzed, this is just sort of summary where we are, right? We have this hypothesis left. That load balancing doesn't help because there's almost no processor starvation in this experiment. So let's do another experiment, right? We're going to run one to sort of go down this new hypothesis. Right? So now I'm going to take a step back before we get back to looking at the new experiments, right? One of the ways of describing this is it was an experiment, or sometimes it would in fact be what I would call a pilot experiment. And I strongly recommend pilot experiments where you choose a smaller set of data, a smaller problem, and you test your hypothesis there before you go run something that takes a week. Right? You run something, test it, checks out your ideas. And it's also good, forget this, right? It's also just good to test that it works, right? That the code runs, it does everything it should. It's sometimes tough because when you get something like this where you've got the opposite of what you expected, my first instinct and most of my students' first instinct would be, what's wrong? A coding bug sometimes, right? I miscoded something because I didn't get what I expected. You got to balance that hypothesis with, like, the hypothesis is something's wrong in my code with the experimental design is not measuring what I want. So the important thing to remember is it's not always your code's fault. So a good experimental design is something that allows you to actually test that the code is working, right? So if I had, for example, one process, right, and I just run it all entirely by myself, right? I should be able to predict there's only one job that's running at a time. I know exactly what's going to happen, right? Then I should be able to double it and do a few games where you check what's supposed to happen, make sure that your code is doing what you want, which is a separate test. Good local module testing is important before you get to a big system test. But I will comment, lots of students put it all together and then run it and hope that answers their questions. And then when they don't see what they expect, they have no idea how to debug it. So design your code with some modules that test pieces along the way. So as we said, right, our experiments, the independent variables were not set in a way that produced starvation. So we really couldn't test because it was load balancing better, because the load was pretty much balanced everywhere. We use pilot experiments to sort of adjust the independent and dependent measures to sort of see where the protocol works and provide some experimental ideas so we can go do our statistical tests. I don't consider this really cheating in a way, right? I'm not trying to test my hypothesis. I'm trying to find out the region of space in which my hypothesis, after being refined, is now. So we know we weren't starving, so we now have a different range of parameters we want to test on. Now we have to go run a new experiment with that test. We don't just say, okay, I'm done, I got my hypothesis, right? So, but it does look like that COSO star is balancing this much better, because the variance of this, if I scale them, it becomes much clearer. These are much more consistent. They're almost always in the same range in terms of what's going to happen in terms of the process of Q-length. But that doesn't really have an effect. So you can then run an experiment with varying numbers of processors in the rings, 3, 9, 10, 20, right? In this case, I'm not going to go through the data. In their paper, right, there's still no significant difference. So changing the number of nodes doesn't actually change things. So actually in those other queues, right, you still have this problem with there are some times when there's a little bit of starvation, but not a ton of starvation. So you're not going to get as much. So what would it mean if I had lots of processor starvation? So if I change the parameters, I can make it starve, and then what do you think actually ends up happening?
You make it too big, neither algorithm will work because it never gets around to executing the process.
No, starvation is the opposite. Starvation is like, I have nothing to do.
You're bored and you have nothing to do. Okay.
So if I have significant starvation, it turns out both algorithms are the same because like there's nothing going on, right? So there might be this narrow little area where COSO star is better, where I have just enough starvation to matter, but not so much that the system's generally idle, so it's not doing much.
Sorry, my brain's having to add the ER to process.
So it turns out that the hypothesis about like always being faster may not work out. So now it turns out that when you're looking at lots of problems, let's come back to this difference between mean and median, right? If we look at which algorithm runs faster in a batch of problems, but it depends more on the problems than the algorithm, which is really what we're talking about now, right? For some set of jobs, one's better, but most of the time it depends on the problems, not the algorithms, because the problems are what's driving it. And in this case, right, these weren't real problems. These were all just made up test runs, so it's really hard to draw anything about it. But it turns out that in these kinds of problems, the variance-reducing transformations allow us to get back to the algorithms themselves, right? We actually saw that one algorithm was on the median faster and the other was on average faster. So we have two different things. So what really matters now is how often does the real world throw outliers at it? Because that's what's affecting what's going on here. So there's no really easy way without running a benchmark from real data to argue about the real world. But one of the things we can try and do is convert things and understand what's going on from a variance point of view. What's making my experimentation vary so much? Because if I can control that, that will actually help. And I will tell you, a big part of experimental design is all about how do I control variance? Because if I can control the variance, then I can make better and better decisions about what's going to go on. So if I look at what causes it to run, right? So this is exploratory. We're sort of looking at stuff, right? So as we look at these, we have different numbers of processors, 3, 6, 9, or sorry, 3, 6, 10, 20. And in the green, we see COSO, in the red, we see COSO star, right? We'll notice that as the number of processors, or processes grow up, right, the two lines between them start to diverge, right? Small number of processes, not much difference. A lot of variation along the line. But as the number of processes get large, then the two curves start separating. And notice that despite the fact that COSO was faster on average, its line has a higher slope. It actually has, this is size and this is the runtime, right? So its runtime is getting larger as I scale up the number of processes for the number of processors. So we can then start looking at that and sort of say, okay, what can I do with that information? So if I look at them and I plot them a different way, here is the number of processors and here's the amount of runtime, right? They sort of all go down as I increase the number of processors. And the green one, COSO, right, eventually becomes a little bit faster we get out here. But COSO star is the green one. COSO, the red one, right, eventually is larger with a larger variance. But these bars, which are common in plots, right, and the standard for any good science paper is bars, unless they say otherwise, are 95% confidence intervals. So you take the plus or minus 95% of the data. That gives you a variance. And one of the reasons that's useful is basically if the bars don't overlap, then it's probably statistically significant. Not always, depends on the number of samples you have, but it's often a good indicator that it'll be significant. So looking at the plot this way, we really don't see things. So the question is, can we transform the runtime with some function of the number of processors and the problem size? And this is often a real problem experimentation, especially with small numbers of data, where you basically get into this problem where I have so many independent variables, things are all mixed up, and it's very hard to draw a conclusion because I expect as I increase the number of processors for the runtime to go down, right? I have a fixed number of jobs, and the more processors I throw at, everybody's runtime is going to go down. But that also means that I expect a lot of variation over the entire set of data because my data has small number of processors and large number of processors. When I run statistics, those variations will kill me. So how might I transform things? Any ideas? We'll go back to this one, right? Any ideas from this? I want to transform stuff so I see less variation as I vary the number of processors. So does anything strike you about these plots? Yeah, that's true. Anything else strike you as a plot about this plot? So a plot like this to me screams there's a relationship. Why? Yeah, it's linear, right? There are lines, right? We didn't start off saying, I'm going to plot lines, right? We plotted data of the size of the problem in the runtime, and it turns out to be linear, right? So if you plot stuff and it turns out to be linear, that suggests that two of your variables are linearly related, right? It's a lot harder to look at this plot and draw that conclusion. So a separate lesson to learn from this is it's often very good to take a bunch of your variables, especially when you're trying to reduce variance, but in general, to take a bunch of your variables and plot them against each other in different ways, right? Because if you find a pattern you weren't expecting, now, if you think about this, you can actually reason why that should be the case. But sometimes you're not reasoning, you just want to observe stuff in your data so you would find that. So if we look at this, right, if I look at S as the number of tasks to be done, N the number of processors to do them, and T the time to require them all, to do all the work, right? So the theoretical best runtime, perfect parallelism, right, would be I have SI divided by NI to get some task done, right? And so if I take TI, which is the number of tasks for task I divided by KI, that's how much worse than perfect a particular runtime is, right? So I can measure things. So if I transform stuff into a new variable R that is going to take T, the number of things to be done for processor I, times N, the number of processors divided by S, I get something that is independent of the number of processors and the size of the problem, both of which drive my variance, right? So we expect it to be, right, if I have N jobs in a divide, right, this is the linear relationship we're seeing. If I increase the number of processors, right, then things will get faster linearly in the best case. Now, does it always get better? No, because Amdahl's law and other things kick in, we don't get perfect parallelism. But that gives me some range looking at it. And similarly, if I take the total number of tasks and I divide by the actual number of jobs that go through, I get things to slow down. So now if we take this new modified variable and I run a bunch of trials and I look at, in this case, we're going to look at the cumulative distribution function over a whole bunch of trials. So the cumulative distribution function is a way of looking at, okay, how much was the probability of this event, the probability of the next event, and I add up all the events as I go through some number of trials. And in this case, we see that the CDF of COSO star is smaller, right? And if I look at them in terms of the mean and median now of this new variable, R, we'll see that COSO's mean is 1.6 and the median is 1.18, where for COSO star, we're at 1.4 and 1. And R, as a variable, right, if I was perfectly efficient, perfect parallelism, then R would be 1. It's not quite 1, but at the median level, it's almost perfectly efficient. So on this new variable, forget this plot for a second, I can just look at these, and now we have consistent representation between mean and median. We've actually dealt with the outliers, because the outliers, so we're faster in both of them, the outliers through this normalization are going to be taken care of. When I have less jobs to do, I'm going to divide by a smaller number of tasks. So when I have less tasks, the efficiency rating is different than when I have a large number of tasks. So that helps reduce our variance, and we get, I'll come back to the CDF stuff in just a second. So again, coming back to these variables, right? By choosing to transform our independent variables into a slightly different form, our dependent variable, which is what we're measuring, right, is now in a transformed space. And that space is one in which we expect there to be less variation, less variance, and that makes it a whole lot better. Now, we haven't gone into statistics, whatever, but I'm going to briefly go through sort of how some of this works for this particular case. We'll have a whole other lecture on the general set of statistics. So if I'm now back to my hypothesis, so my hypothesis, I'm going to assume that COSO and COSO star are the same, which is the classic. We actually assume the opposite and then prove it's not true. So I'm going to run an experiment to run these simple statistics. So I have the means here and the delta in the means. So I can talk about the distribution of the difference, delta, difference in means, given the assumption that those two distributions should be the same. That's what a statistic test generally does. We can find the probability of that if we assume that, and then if the probability of this is very low, we reject the assumption that they're equal. So we pretty much assume they're equal, use that to estimate a probability, and then if that probability is very small, we reject our hypothesis. So if we use 0.2 as our residual, normally the two values are 0.01 or 0.05, but 0.02 is a perfectly good residual. We can test the variance of the means, and we find out that it is. Again, how to do all this we'll talk about in another class. And it turns out that the reasons that the variance is so important is in this kind of statistical test, I look at the difference in the mean, and then I divide by the variance. And the variance is what drives whether or not this test is significant. So when we had the early version of the mean, nothing was significantly different because in part the variance was so large that even though the difference in the mean was there, it was dominated by the variance. The variance was very, very large. So this is a particular test, this is the t-test, but in almost every statistical test, if there's a lot of variance, you'll have a hard time drawing any conclusion because you're actually trying to answer the higher level question, could the difference be caused by the random variations I'm seeing in this variable? And so if I have my variable, and my dependent variable has a lot of variance, then I can't decide that the difference I'm seeing in this dependent variable isn't caused by the algorithms being different, or if it's just two random sets of variables happen to come out that way. So every time we go through this chart, we want to actually try and reduce the variance in our dependent variable.
Where did we derive our estimated variance between the means, the denominator?
So where did this come from?
Yeah.
Right now, this is more statistical test later in the semester. We haven't derived that yet.
Okay.
This is, right. I'm trying to motivate statistics before I teach you statistics, because if you see why you might care, then when we start deriving it, it becomes much more useful, as opposed to teaching it here's how they work, and then we'll get there.
Different types of t-tests.
Yep.
as well.
Oh yeah, there's lots of types of t-tests, and then there's ANOVA. We're going to do a whole bunch of testing stuff later. I'm just sort of simultaneously trying to motivate. We want to be able to draw these conclusions, but almost all these conclusions depend on the variance. And so if you can't control the variance of your problem, you will have a hard time drawing any conclusion. This is also why, in lots of theses and lots of other people's research, I struggle when people show me a curve and say, see, my algorithm is better than theirs, right? I can't decide that. If the curve is anything other than a straight line, in my head, I can't compute any relationships to decide whether or not it's important. Because as soon as there are variance, this divisor is really hard to figure out in your head, and then figure out, is anything going to be statistically significant? So to me, I like to do tests because it works things out. So in this particular example, the difference between these two means and the standard deviations of the data allow us to now actually draw this test and actually conclude that COSO star in this new metric is not just better, the mean smaller, but the difference is statistically significant. It is not a random chance, where it's a very low probability of random chance. The fact that it's less than 0.02 means there's a 98% chance that if I ran 1,000 experiments, right, 98% of the time we'd expect COSO to win. Not all of them, right? And that's, again, important for computer science. It's easy to run an experiment where one or two cases you fail, right? So if there's that little bit of starvation, right, then you might win one. But most of the time, COSO is going to win. Sorry, COSO star is going to win in the testing.
So you're using the differences in the standard deviation. Is that right?
So actually, these are the individual standard deviations. So here we're taking the standard deviation of the values paired together, which you can't get from either one of these. There's no way to get these two numbers on that. That is the variance of the differences, right, which is. So here we have the mean, the differences of the mean, which, because the way mean works, is the same as the mean of the differences, right? Because it's a linear operator. But variance is a nonlinear operator, so I can't take the difference of the variances to mean the variance of the differences. It's more complicated. So yes, that was a little bit of shorthand, sloppy. We could have done it, but it works out the same. But really, the important thing, we'll talk a lot more about how to do statistics later. I just want to sort of get you to understand that one of our goals in doing an experiment is to be able to draw this kind of conclusion. And if I did the same test for the original data where we just talked about the mean of the speed, it would fail. And this is a place where lots of students, unfortunately, in my view, struggle with their experimentation in their thesis, right? If you really have a good hypothesis, this idea about load balancing for COSO star was pretty intuitive, pretty obvious, right? It's already been published, so you can't have that as your idea, but when you have a reason to believe in your hypothesis, sometimes the difference is how you're analyzing the data, not that your hypothesis is wrong. Digging deeper, this is why I said you often run an experiment, you get some results, and then you change it. So the one thing I didn't say, what is the new hypothesis that we're looking at for this test? So this is sort of what's going on. What's the hypothesis? Before it was that this was better because of load balancing. What have I changed my hypothesis into? Nope. As soon as I transform the variables, I have to transform my hypothesis. So I'll give you a hint. Well, actually, so our goal was actually not talk about particular load conditions, right? So here we transformed it, right? So our new hypothesis is actually that this transformed variable, which is really the relative efficiency of the algorithm, is, for COSO star, is a more efficient algorithm with this measure of efficiency than COSO. Right? It's not about average time, it's about how effectively am I utilizing the processor. Which actually comes back to your first comment, right? If I look at this as utilization, R and utilization are reciprocals of each other, right? One is how efficient am I, the other is what's my overall utilization, right? I could probably have drawn another way of getting to this by looking at the utilization. But the reason people often talk about a particular variable in their paper is that's the variable that lets them reach the conclusions they want to do. They really wanted to say on average it was better, but it wasn't. Right? So you change it so on average it's more efficient. Right? It's just definition of better, right? It's not shorter runtime. In fact, from a Amazon's point of view, what do they care about? Do they care about your average runtime or their system efficiency? They actually care about efficiency. So there are lots of places where that's the right variable to look at. So, but as you go through this, I wanted to just make sure it was clear that we change those variables. When we change the variables, it matters. So it is and it isn't. So we basically made a new hypothesis about R, and then we ran a new experiment to verify that it was true about R. Right? I wouldn't want to compute a variable for my. So that's the important thing, right? I can't just go to the old data and say, oh, look, if I fit this function to it, now I get these results and it explains my data. That's not good science. Good science, you make this new hypothesis, you go out and you run a new set of data, and you'll get this result. So it is an important point. Now, the other part of that is it bad science? So what it's really saying is your initial gut instinct, your initial hypothesis wasn't quite correct, right? You had the right intuition, but it wasn't right for the exact right reason. It wasn't about load balancing. It was actually about overall efficiency, right? So is it good? You now, if you did, here's our hypothesis, we ran the experiment, we collected new data, we measure it, then yes, it's good science. Because you now say, I can explain why this happens. Is it your initial guess? No, but that's okay. What you don't see in lots of papers is how often that happens. They originally start off with some hypothesis, they run experiments that doesn't fit their data, they figure out a new hypothesis that goes on and do it. And their biggest question is, did you rerun the experiments? And if you did, then it's perfectly good science. If not, it is questionable science. It's probably still, unfortunately, publishable. So I'll be honest about that, right? There's no doubt you can present it because they can't really tell, did you run a new experiment? Or did you just say you ran a new experiment? There's almost no way for them to tell. But my recommendation for your long-term career is run that new experiment because you really don't want to make it sound like you ran one, and then later on find out, oh no, that was just an artifact of our data. It happens.
But I mean, technically that's part of the scientific method process is that, you know, all of your hypotheses are not going to be correct.
No, in fact, most of them will not be, right? So that revising of the is a perfect normal thing.
You're wrong, you do it again.
Hopefully you get closer. So hopefully it's a spiral, not just a loop. You spiral. Oh look, that was right. Hey, I'm done.
We're doing stochastic gradient descent.
I was going to say it's like super Sisyphean. If you come back to the start A, you never actually get further or closer to your destination.
So we actually have a very related process we call graduate student descent. And graduate student descent is where you keep modifying the data, right? So another possibility is that literally the algorithm doesn't quite work, but I will find the data on which it does. Okay? Or
create my own data set.
Or even if I run train and test. So a good statistician would say that you're allowed to use your test data once. If I use the same test data, so I have my algorithm, I make some tweaks, I do some work over here, and then I test it over here, which is a common thing in machine learning and AI. We have a training set and a test set. Really, I shouldn't use my test set more than once, because if I eventually train again, no, that didn't work, train again, I will get, eventually, if I try enough variants of my algorithms, I may get one that on this test set wins. Right? But it's no longer this random test. In fact, that is what this entire rather long XKCD comic is about. I will not expect you to read it, but the top line is jelly beans cause acne, and they asked the scientists to investigate. Right? So, we found no link between jelly beans and acne. Probability 0.05, standard statistical test. Right? No. I hear it's only certain colors that cause it. So scientists go run your test again. So then they run, nope, no correlation between purple, nothing with brown, nothing with pink, nothing with blue, nothing teal, salmon, red, turquoise, green, jello. Oops. Keep going, and eventually we found a link between green. Okay? This is a classic abuse of statistics, right? If I run a test that has a probability of being correct 95% of the time, and I run it 20 times, right? I'm going to find one.
One is going to be 95.
And then I've drawn it. So this is actually the other place that graduate student descent ends up, right? If I modify my algorithm 100 times, and I keep testing on the same data, I may actually find one that works for that data.
Chance I'll do it.
So not only do I recommend that you rerun your algorithm, I will actually recommend you run your algorithm on new data, not the same one over and over and over again. Because otherwise you can draw a conclusion that really isn't general. You just happen to run enough random variations of your experiment that it eventually happens to be true. And that's all statistics will tell us, is that the odds of a random set of experiments happening is, in this case, 95%, right? So if I run it enough times, I can find that one sample that fails. Okay, so this is going to talk a little bit about.
Sorry.
Oh yeah, actually, why don't we take a 5-minute break and then we'll. It's a good spot to stop. So the first survey paper data set paper, that was really your job, day job, right? North Dakota, wherever?
Nebraska.
Nebraska.
TLDR, they're like a startup underneath the university, and we were seeded by a billionaire. So eventually we started running out of funds, and they're like, hey, we need to go make money. I'm like, okay. So they had me submit a proposal to Cisco. Cisco gave us time to pay for it, we spent the whole year on it, which really turned into I spent the whole year on it. So yes, it's been my day job for like the last year.
So is there still a value for your data now that you've seen that other? Because last week you weren't sure because you just found the paper.
It's arguable. I don't. When I went into it, it seemed a lot clearer whether it was going to be useful or not. Now I'm not so sure, and I don't really have advisement or mentorship that can tell me if it's useful. Like I'm not a GAN specialist. I don't know if the way that we formulated our data set is particularly useful to people studying the decision boundary for intrusion detection machine learning algorithms. I don't know. I do know it seems like we're the only people doing IRB. It does seem like we're the only people that had pen testers evaluate their own ability and discuss the strategy over the network traffic that we're giving openly. I don't know if that's useful. There's 10 people, like, is it statistically significant? No. Could it show us interesting things about the data? Yes. Is it human generated instead of network algorithmically or programmatically generated? Yes. And it's extremely noisy. Like this, it's real. But like I'm trying to motivate how this is important, and I don't have the expertise to say yes, it is important, or yes, this is valuable.
You know what the company does?
No, they're like, hey, you seem to know some stuff about machine learning. Do you want to basically do machine learning for us? And it's like, okay, I'll do all this stuff. But like, who am I asking for things I don't know?
So let's schedule a meeting. So this is one, I'm not taking on new students.
I figured you weren't. It sounded like you had quite a bit on your plate.
But it's an area where, one, I do know a good bit, and two, I also know other people, so I might be able to help hook you up with like a student who's graduated, who is a mentor who currently works for 23rd, so 2 days he works for FireEye. Currently works for Sophos, but he does machine learning for intrusion detection stuff. Right? That's what his focus is. So he might be able to answer He loves to publish, so he might be interested in doing his own work or whatever. He has his own startup company in addition to working for the big companies, right? So he just done some projects with him like the SBI or CTR. So he was very careful when he was on his job search. Like this is one of the upfront questions, right? Can I do something? And what's funny is that
I've actually run into that same
oh
problem.
yeah, it's quite common. We own everything, right? Lockheed Martin,
Pretty much.
right? Pretty much. If it's code, we own it, right? If it's related to code, we own it. If it's not, we might still, but we'll give you some chance of owning like
If
a
you had a
snowboard.
shower thought on your day off when you're on vacation in another country, it's ours.
That's how my family works. Effectively, I have to submit paperwork if I ever want to advance an idea and possibly even find it. Usually it's just live.
It's been nice working, it's been nice in this one particular area and a complete nightmare in others to work in academia. It's like if you have something else on the side, you just declare it. Usually they're pretty cool about it as long as it's not conflict of interest. I cannot say the same thing for any defense contractor or really any of the security companies. I've signed so many non-competes, it's kind of sad.
Not all universities are, so lots of
That's
universities are, we own it all.
Yes.
Some universities are like, we could care less, it's yours. Lots of them are in the, you have to disclose it, and then they have a process. Some of those processes, like CU's, is actually pretty, when I interviewed, before I came here, I interviewed like 12 students. And it was one of my quite common questions, that people are like, why are you interested in this stuff? They knew there was somewhere I wanted to do it. So CU, they have 6 months to answer that question, or it reverts automatically.
Oh, so you win.
So you win, right? So it's like they have
That's
6 months to
awesome.
answer the question, or it's yours, right? Otherwise, they can just sit on it forever, right, and
Yes.
never answer the question, right?
Yeah.
So an important thing to ask when you look at those jobs. And I've had 4 inventions returned to me now. Two of which are like, okay, it's a game, it's a snowboard, right? That's like completely outside of what I do. 2 of which are like biometric related stuff, and the other was machine learning, what we just did last year.
Trying to
And they're like,
cause problems.
they don't see a financial benefit in going after it because patents are really about financial, right? And so my view is like, look, literally at a gold publishing, right? If I have a student that has a patent that gets them lots of citations that will help them get a job, right? It doesn't matter if we will never enforce it, right? It's $1,000 for me to patent myself. There's also the trade-off, right? If the university patents it, it's like 10 to 20 grand. If I do it and I work with a student, he learns about the process, and we get a patent, and it's under $1,000. So it's an easy win for me. It's like, okay, you're going to learn all this stuff. We're going to do all this, and we'll go through the process. It may not survive. The patent may be invalidated on this first, court case if someone goes to sue about it. But that's not why I'm doing it. I'm doing it to teach my students.
Still the process. Yeah, the process is important. It's not profit.
No, well, we have stuff where we teach that. So I like to make sure we do more of that. Okay, so I'm going to go ahead and get started, but I'm going to start. I forgot because Roger wasn't here yet. He's been here all class, the last class. I didn't talk about your next assignment, so I'm going to stop. Actually, let me stop recording just so I get it in a good spot.